There's something strange happening in the universe. Over the past few decades, astronomers have detected a perplexing shift in the behavior of light from the most distant objects in the cosmos: quasars, pulsars, and ancient galaxies. Observations suggest they're not just far away, they're also slowing down. But not in motion, in time. This isn't about expansion speeds or gravitational pulls. It's about how time appears to behave differently across the observable universe. And the deeper we look, the more puzzling it becomes. This is the enigma now called the Great Slowdown. We've long known that light from distant galaxies is redshifted. The farther the source, the more stretched the light's wavelength becomes, a hallmark of the universe's expansion. But subtle clues buried within that light suggest something more. Not only are these signals redshifted, they seem drawn out, as if the events producing them are playing out in slow motion. First noticed in quasars, the intensely bright galactic cores powered by supermassive black holes, researchers found that their flickering, once used to track energetic activity, seemed oddly stretched when viewed over vast distances, as if the activity itself was operating on a different clock. Some theories emerged quickly. Perhaps this was simply a natural result of time dilation from cosmic expansion. After all, Einstein's theories predict such effects at high velocities and immense scales. But the numbers didn't fully match. The slowdowns were too pronounced, too consistent, and strangely out of sync with what our best models projected. Other anomalies began to surface. Supernova light curves looked subtly off. Patterns in cosmic microwave data hinted at temporal asymmetries. It began to look less like a measurement error and more like a challenge to our understanding of time itself. Some scientists proposed that the constants we thought were unchanging, such as the speed of light or the gravitational constant, might actually evolve over time. Others turned to more radical solutions: new physics, possibly involving higher dimensions, or time emerging from quantum interactions. Each theory raised more questions than it answered. Few cases exemplified the mystery better than a 2023 study comparing quasar variability across billions of light-years. The farther away the quasar, the slower its fluctuations appeared. And not just because it was far. The slowing followed a curve beyond what redshift could explain. Something deeper was at play. If time truly ticks differently across the cosmos, our assumptions about causality, measurement, and cosmic history face profound implications. If this topic interests you, you might enjoy the other stories on our channel. You can subscribe to explore them. One leading explanation points to a conceptual shift in cosmology. Instead of viewing time as a universal background rhythm, some theorists propose it could be relational, defined only through interactions, and possibly variable depending on scale or gravity. In such a view, cosmic time is not absolute. It's emergent. Another theory draws from high-energy physics, proposing that time arose from entanglement. In this model, the universe began with no time dimension at all. Time emerged as systems became thermodynamically complex. If true, the Great Slowdown might reflect a deceleration of that unfolding process, a kind of cosmic cooling of time itself. But every answer spawns new questions. How do we test these ideas? Are we misreading the data entirely? Could new surveys, like those from the James Webb Space Telescope, offer clarity or deepen the puzzle? For now, the Great Slowdown remains one of the deepest unknowns in astrophysics. It forces us to ask, is time a constant flow or a shifting shadow across the stars? The truth may reshape everything we think we know about the universe and our fleeting place within it.